All right, welcome back to the afternoon session. Before we do the introduction of the next keynote speaker, let me first do a bookkeeping announcement. So if you're coming to the conference dinner tonight, make sure you bring your badge here, or if you have a guest, your banquet ticket, that's required for entry. All right, but now it's my great pleasure to be introducing Michael Jordan as our keynote speaker for today. He's a professor in the Department of ECS, of Statistics, and of Industrial Engineering and Operations Research at UC Berkeley. He's been the chair of statistics there, but where he's actually spending his time now is at INRIA in France, doing research there. Michael is one of the pioneering figures in machine learning with foundational contributions from Bayesian inference to deep learning. He's won major awards in pretty much any related discipline to machine learning and economics. He got the Granada Prize from the American Mathematical Society, the IEEE John von Neumann Medal, the ICHCAI Research Excellence Award, the Rumelhart Prize in Cognitive Science, and the ACM IIII L. Newell Award. He's also a member of the National Academy of Sciences, the National Academy of Engineering, the American Academy of Arts and Sciences, and a foreign member of the Royal Society. A common thread that goes through many of Michael's work is the connection between machine learning and economic models of behavior. Michael is not a regular here at the RecSys community, but his work is highly relevant to how recommender systems function in an interplay between the stakeholders, from users to content providers to platform operators. And this view will become ever more important, I believe, as AI systems go beyond recommendations, but take larger and larger roles as actors in our society. My personal view is that recommender systems are only the beginning of the next generation of widely used AI systems, and that this generation is not far in the future. And we as a community, I think, are very well positioned to lead this new generation of systems. The lessons we have learned on AI and that, how AI interacts with the real world, the methods we should develop should and will have profound impact on the next generation. And the connection to economic models of behavior is an important part of that toolbox. So without further ado, I'm looking forward to Michael's talk on a collectivist vision of AI, collaborative learning, statistical incentives, and social welfare.
All right, thank you. All right, it's my pleasure to be here. As you will see early on in my talk, I feel a real affinity with this community. I do have the phrase, not recommendations, but AI on my slide. I think it's the first time I've ever put AI on a slide, and I'll sort of say why I feel compelled to. But this word collectivist, I think, gets closer to what this community has been about. And I thought that was a great introduction, so thank you, Thorsten, for inviting me, and thank you for the introduction. I agree, we're kind of looking, especially in the young people in the audience, we're looking for thought leaders. I think we have we're missing thought leadership in AI these days. Silicon Valley is not providing thought leadership, so we're hoping that some of you will stand up. So some of the people that have provided at least some thought leadership back in the day, these are some of the big picture academic visions. Cybernetics, Norbert Wiener, mathematician, kind of looking to do something more with information, and he had kind of a notion of networks and intelligence arising through control theory and so on. So maybe the closest of any of these three to this community. As you all know, John McCarthy introduced the phrase AI. He was interested in kind of singleton intelligences doing logic in their head. And then Douglas Engelbart, kind of a father of HCI, thought of computers as augmenting our intelligence. And so the search engine and the mouse and all, that was Engelbart. Frankly, I think of all these three, it's really it's Wiener and Engelbart who really laid the groundwork for the era we're in the most. And sadly, the phrase AI unfortunately got affixed to their work. All right, now I don't really think that's the right way to think about what's happened. So indeed, I've called myself machine learning for all these decades, and I think most of us in the field have. We were alarmed when the AI buzzword was brought back and affixed to our line of work about 5 years ago. It was a PR stunt, frankly. But in the real world, forget the academic perspectives for a minute, kind of what happened. Well, there were companies that had massive amounts of data circa 2000. They were building models so they could predict things and then make allocation decisions in the real world. And so I particularly have in mind Amazon, but you've got Alibaba in China. You've got companies around the world that were doing supply chain modeling at vast scale. And that's why we have companies now that can take 1 billion products and serve it to hundreds of millions of people. You could never do that with old textbook methods and with somebody working with a computer. It had to be massive data and massive predictions. So for them, it was random forests. That was the technology of the day. So at Amazon, everyone used random forests for everything. And random forests were big, lots and lots of parameters, and the data sets were massive. This was supply chain modeling. So it's like every product had to come across the ocean, but not just that, the parts had to come across the ocean. It all had to be put together quickly, it had to be inventoried, stockpiled, so that nowadays we have a system that's the world's largest stochastic control system, takes pieces and labor in, puts out products, and within a day or two it'll go to any door in the world mostly. It's amazing. That was all done with machine learning. It was all done with random forests. And they couldn't do it just on one computer, so they had to build a cloud, and they did. They didn't call it the cloud, but it was the cloud. That's the origins of the cloud, actually, is running random forests on supply chain data. It worked really well, not just over time you saw it working, but it was interesting. It delivered solutions to supply chain problems that people hadn't thought of before. To be the next generations, that same company and related ones realized, oh, we don't just have supply chain data, we have transactional data. We have data. Thorsten comes and buys some books. Mike arrives later and buys some of the same books. Let's make a model of that, a big matrix. Let's do recommendations. Now, how did they do recommendations back in the day? Well, they used random forests, and they did it on their cloud. So nothing really changed in the architecture or the methodology. The data's changed. And now they started doing recommendations, and then other methods arose, and it's ongoing, which you people have contributed to. But anyway, to me, it was bringing in, what was new is only that there was transactional data. So it was a little bit of a human side to it. It was a social side, even though very implicit. Big success. The first 2 layers are big successes. Third generation, what's changed? Well, scale has gotten bigger, and now in the cloud, you throw in GPUs. GPUs like neural nets better than random forests, so kick out random forests and pull in neural nets. But, stepping back a little bit, it's the same. Lots of data, lots of compute, highly networked, data from everywhere. What's changed? The data. Now it's human language and vision and all the human-like things. Run the same architecture, gradient descent-based algorithms, make some architectural changes, do some clever things, and out pops something that can predict very, very well, just like the supply thing, but now it's for human language, and now it looks human. And now we have all the crazy dialogue and hype that we have that's very mostly misplaced right now. All right, now if that was the end of it, I'd just be telling this story as like a journalist, or historian looking back. It's not the end, it's the beginning. So what's happening in this era to me is not the super intelligent system that answers all of our questions. It's rather the emerging markets. What's a market? Well, a market's a social phenomenon. It brings people together, it links them in various ways, just like a recommendation system. But markets are more than just recommendations. That's the main point of my talk. Now, let's return to academics for just a moment. How do you build systems that do markets at vast scale? And I think these things exist, by the way. I do think that Alibaba, Amazon, all that are building markets at vast scale. You've got all kinds of people involved, producers, consumers, deliverers, and then products, and money's being made without advertising, and so on. In the academic world, you need 3 styles of thinking, and I put names on this: computer science, economics and statistics, just to have names, but it's broader than that. And those fields have gone on since Wiener. That's kind of the era those fields became rigorous. But alone, they solved last generation's problems. The new generation problems aren't really in one of those fields. So you would say, okay, if academics looked at blends, and they have it in a very simple, limited way. So statistics meets computer science. What is that? That's just machine learning. Okay? I'd say mostly statistics with the help, even not so much from computer science, really from optimization theory. But it's healthy. But what is machine learning missing? Economics. The third leg of the simplex is mostly not present in machine learning. We don't have a lot of talk about incentives and so on. We have kind of vague talk about fairness and bias and all that. Economic concepts are not really being treated correctly. What about statistics meets economics? Well, that's econometrics. What is econometrics missing? Algorithms and mechanisms that act on the world. It's mostly about measuring the economy and saying something for macroeconomists to help them understand the economy. What about economics meets computer science? That's a field too. That's called algorithmic game theory. What's it missing? Well, almost no statistics. It's mostly about auctions and other kinds of mechanisms for allocations. You run those mechanisms, you don't learn from data, mostly. Again, these are a little bit caricatures, but it's mostly true. Long story short, pairwise interactions have emerged, but you really don't have a three-way interaction very much. Most communities have not really kind of grabbed that. On the other hand, if you go to Amazon or Alibaba and you watch them solving problems around the table, we're building a market. There's third-party sellers here, there's people here, there's all these things. You have people from all these communities, critically. And the solutions that are proposed have ingredients from all three. Okay, so AI is supposed to kind of solve all these things for us. So I am going to sort of, hint at the limitations of AI here, but really, hopefully, the talk will be more of the positives. What other things can we do? But I don't think that the current dialogue on AI mostly talks about collectives. Now, implicitly, ChatGPT and so on is reflecting collectives. It's taking data from everybody. And I think to the extent it's at all smart, it's mostly because of that. Lack of a focus on uncertainty, lack of focus on incentives. Let me dig into this a little bit. Uncertainty. If you ask ChatGPT, you just told me something, how sure are you of that? It will say something, and it'll sound plausible. Usually it's either very sure or very not sure. All right, but then if you continue the dialogue, you say, well, you're sure of that, but here's another piece of evidence, or I was thinking about it this way, it'll change its mind completely about its uncertainty. It's not reasoning on uncertainty, it's using past data to sound like it's reasoning on uncertainty. Okay, to me that's worse than not doing logical reasoning or whatever. Because if I interact with the real world, I need to know all about the uncertainties. If my doctor tells me something, I need to know how sure you are. That's what humans really need to do to go forward in life. It's a terrible partner in that regard. Just to quantify that, here's just a figure out of a paper. Estimated confidence agreement with humans, you should be on the 45-degree line. If you look on the right, you will see that ChatGPT is very sure of itself. It says 1, or it says 0, and then occasionally it says something around 50%. That's his version of uncertainty. Very, very poorly calibrated. Now, do humans cope well with uncertainty? This is a long philosophical debate. There's arguments that we don't. I would argue that misses the whole collective story. As an individual, I'm not very good at dealing with uncertainty. You put me on a desert island, I will be messed up. I won't be calibrated. You put me in a city that I don't know very well, I also don't know. But as soon as a whole bunch of people are around, I can look at them and say, oh, that person probably knows. I can go and ask them. And they may indicate they're quite sure, or they may be having some uncertainty. As a collective, as a culture, we mitigate uncertainty. Okay, our knowledge mitigates uncertainty, but also our markets mitigate uncertainty. Okay, that's the critical point of my talk. If you don't build mechanisms like AI that enter into those kind of entities, you are not helping with uncertainty. You're only probably making it worse. All right, so let's think about this for a moment. Collectives and uncertainty, is that a kind of a topic? Well, think about a decision maker. Here we have a duck who's trying to decide whether to go to the left or to the right of a lake every day. They've done some statistical analysis in the past, and there's twice as much food on the left as on the right, and so they're trying to make a decision for tomorrow and the following days, where to go. Let's suppose they're sure at this point they have good confidence. Well, the Bayesian optimal decision is to go to the left because there's more food to be found there. So a Bayesian optimal duck would go to the left, and they'd keep doing that and get a lot of food. Actual ducks don't do that. They go to the right often. In fact, they do what's called probability matching. They'll go 2/3 of the time to the left and 1/3 to the right. So the argument is that ducks are just a little bit dumb. They get, wowed by the food over there. And interesting though, if you do the same kind of experiment with humans, not with food, but with other things, people probability match too. So then the argument is that people aren't Bayesians, we're not good with uncertainty, all right? But that's missing the point. The point is that if there are many ducks that were in a group of ducks, which is the more realistic evolutionary situation, right? Then if every single duck is a Bayesian and goes to the left, then there's scarcity. You run out of food over on the left, there's all that food sitting on the right. So how do you do the allocation? No one's going to tell a duck where to go. So the right mechanism is, in fact, 2/3 of the time I go to the left and 1/3 I go to the right. That actually is a Nash equilibrium. Okay? And people have argued about this thing for a long time. They said, well, I'm a machine learning person. What this is exploitation, exploration. They're not sure it's a bandit algorithm. There could be food still on the right, so I got to go there a few times. That would be just a very few times. It wouldn't be 1/3 of the time. Okay. All right. So I think that this is part of the point: is that we evolved to deal with uncertainty not just by communicating with each other, but we evolved to be in the context of other humans, and our uncertainty reflects the uncertainties of the collective, not of us individually. Okay. So I hope you're starting to see the word collective is starting to do some real work here. Okay, so now let's talk more about the computer science angle. We're building new kinds of collectives. Humans, but also computers are all embedded together. We want information to flow. What can technology do in those kind of situations? Well, on the one hand, it can, in principle, help more information to flow and have compute available to make better predictions. It also can connect more broadly. Okay, but, someone should have thought of this a long time ago. Just because you connect up people doesn't mean that good things happen. All right, so people may not want to connect, or the right people may not connect, the bad people connect, people lie, and so on and so forth. We are not even close to solving this issue. And it fundamentally is mainly an economics issue, meets computing. Okay, so just to say one more bashing kind of phrase about Silicon Valley. I get up in the morning, I'm not on social networks, I don't read much of this, but I read a little CNN or something, and I get just irritated time and time again about Sam Altman and Elon Musk. These are people that I don't really think have a vision for technology. If to the extent they have a vision, what it seems to be is they put all the compute in the world in an entity sitting on a hill, and they run big algorithms on it, and it takes all of the data from humans, and then it figures out the right thing to do, and it spits back knowledge to us humans. Okay? Not only is it not a very good economic model, but it's just not going to work. All right? We do things in the moment. There's no way the thing on the hill is going to know about my every wishes and desires, and we interact with each other. The thing on the hill is not going to see all of that. It's just a dumb way to think. All right, so instead I want to not just have collectives, but I want to have markets, and I want mechanisms in these markets that are computing-based and recommendation-based, but I want them to be market-based too. So there's incentives, also there's asymmetries of information, which is critical in any kind of economic system. All right, so first of all, I have to defend markets. Sometimes, I've now given this talk a few times, people say, oh, computer science is great, we're building nice worlds. Markets, that hurt the world. That led to terrible things. Markets are terrible. They're not. They're a force of nature. You can say we can regulate them, and you should, but you shouldn't get rid of them, and you shouldn't imagine you could get rid of them. They're always going to be there. They came around, way before there was mathematics or technology. What's good about them? Well, they don't just have optima that someone decides on. They have equilibria that is often each individual has a separate utility function, and the equilibria are in that space. They can reduce uncertainty. One of the markets that we all know and love is a market that brings food into a city every day. All right, so in Bari here, somebody has some tomatoes, and they realize that over on that side of the city, there's not enough tomatoes, show some scarcity. They drive over there, maybe they rise their price a little bit, and they sell some tomatoes. Huge numbers of people make individual decisions like that, and the thing kind of works. And it works every year in and year out, day in and day out, for vast amounts of time. It's not perfect, but it does a lot of things well. Now, because I shouldn't have to elaborate on this, but sometimes journalists don't seem to get this. Now, what are the things it does well? Well, first of all, if I want tomatoes, I can kind of guarantee there'll be tomatoes any day of the year in this city. That's pretty cool. But even more importantly, if I'm trying to build a business on top of that, I want to build a pizzeria, I need tomatoes for my pizza. I can guarantee there will be tomatoes every day of the year. So I can build a business on top of that. Someone else can layer on top of that. Again, obvious, but not necessarily talked about very much. Okay, so prediction becomes easier, things are more stable, we got to build good markets. All right, so we got to think about how to build market mechanisms, and just predictions and recommendations are not enough. Okay, we need concepts like incentives, prices, and utilities all embedded in this kind of system. Here's an actual working example of something I've been involved with. It's a company called United Masters. I'm on the board. I helped design the original architecture. But the real leader thought-wise on this is Steve Stout, who is a legendary hip-hop producer. He's the CEO and has envisaged and executed United Masters. It's a three-way market. It's really up and running. It's working. It's been working now for several years. It's revenue positive. But moreover, it's got 3 million musicians signed on who are all making some money, or at least a significant fraction of them are. So three-way market. You got musicians, you got listeners like you and me, and critically, you need money to get into this system so it can be redistributed according to utilities. Where's the money coming from? It's not an advertising story. It's not subscriptions. Rather, brands like the NBA, National Basketball Association, FIFA. Steve went to the National Basketball Association. He knows people there and said, when you do videos, on your videos, there's music often. You're paying record companies for that. Why don't you stream it from my musicians? My musicians are, 20-year-olds mostly, people who are doing some of the music that most young people like to listen to. So use us instead, and so that's what happened. So if you go to the NBA website and you click and you hear music, it's coming from one of these musicians, probably a 20-year-old, and they make money in that moment. It's not, Spotify gives them some money later or somehow. Now, the other brands see that. That artist is seeming to be popular on the NBA website. The NBA website has a certain demographic associated with it. I like that demographic for my products. I'm going to reach out to that artist and ask to work together. Maybe write a song for me, come to our annual meeting, whatever. That is starting to happen now. So young people now who were not getting any money before for doing really great music are now getting something that starts to look like a salary. Okay? So this is a recommendation system under the hood. It's looking at the music and recommending it for sure. Right? But it's also a market-based mechanism. There are along the edges of this graph are incentive-compatible mechanisms. It wouldn't work otherwise. Okay? So 3 million musicians, several hundred brands have now signed up, lots and lots of listeners. It's up and running. It's working in the United States. It's now going to Nigeria and Brazil, and I think it's a model for around the world. Now, it's a three-way market. It's critically a three-way market. If you just do a two-way market, it's not really enough. So Spotify does that. They take music and they stream it to people, and then they make money somehow. Listeners aren't willing to pay. Spotify knows that. So Spotify just, makes some money on subscriptions, and they throw a tiny fraction of money back to the listeners. But it's a low-margin business, so they're incentivized to try to get rid of the musicians altogether. Let's use AI to make music. That's part of Spotify's dream, right? All right, so you critically need three-way markets for this particular thing. I think in general it's going to be true for arts. Okay? All right, so there's no papers on this, but I encourage you to go look at the United Masters website, and you'll learn a lot about this up-and-running market. If you're an entrepreneur, and I go to Silicon Valley sometimes, I say don't just try to build LLMs or whatever. Build three-way markets. Think about what three-way market is underlying your idea. Here's a different kind of three-entity market. We call this a three-layer market. So this is now academic work with myself and Ali Reza Falah and colleagues. So this is a model of a real-world phenomenon. So the real-world phenomenon is this. We have users who are going to platforms, and the platform is taking in data, maybe transactional data, and it's providing a service, so maybe payment. All right? More data the platform can get, the better the service can be. So it's kind of a data market thing. Now, many of these platforms don't make enough money just on the service fees. So what they do is they take the data and they sell it to third-party data buyers. So this happens a great deal. Nothing wrong with it. Why do the data buyers do that? It's not that they want to build a service themselves. Rather, they use the data to do market research of some other kind, figure out what's happening in the city or whatever. All right, now, add an economics story here. The users will look at this, and why should they be incentivized to be in this market? Well, they get a service, but also something's taken away from them, which is their privacy. Data is being shipped to third-party people they have no control over. All right, so if you're going to really be incentive compatible, you should add a privacy mechanism. Okay, so let's imagine the platforms do that. Now, let's not have the government regulate this. Let's make the platforms decide how much differential privacy will I add. I'm going to add, 10 units. Thorsten's going to add 5 units and try to undercut me. All right? Now, that means I will add more noise to the data. He will add less contractually. The data buyers will look at that and they'll say his data is less noisy. Let's buy from him. Let's pay a higher price for him. He likes that, so he gets more money. On the other hand, the users look at the two of us and they say, well, he's providing a better privacy guarantee. I'm going to go there. All right, so I get more users. That allows me to build a better service, and I get more data, and it's a nice, friendly loop. And now the data buyers look at that and say, well, that guy, it's more noisy, but it's more data and higher quality. Maybe there's a balance here. Okay, so I hope you can see this is a tangled set of incentives, and one needs to analyze all of that. And you can. Okay, so I'll come back later to this problem later in the talk and show you, once you learn about incentive compatibility a little bit, about what we're doing here in the three-layer data markets. Okay, so that was the first half of the talk, and I'm about halfway through. Here are some of the problems I've been working on for like 10 years now. And just to sort of, scan your eyes over this, there is some prediction a la LLMs, but not that much. Really, this is about uncertainty quantification, decisions, incentives, bias, et cetera, et cetera, et cetera. Okay, so in the second half of the talk, I want to now get into some technical work that basically says, here's a problem. It has both incentives and learning in it. How do you address the problem? And I will not get into details here. There's papers for all this. You can see algorithms and proofs and also, in many cases, some deployments. But I want to show you the problems that we tried to solve. Okay, so first I'm going to do very quickly this little bit. This is one of the more important lines of work we've done in the last few years in my group. This is more about bias and not so much about incentives. So I'll do a little bit on bias, and then we'll add in incentives in the second part. But just briefly, first of all, these are my colleagues at Berkeley who worked with me on this. They've all gone other places, or almost. But Anastasia, Stephen, Clara, and Tiana, I want to recognize here. Okay, so you all know about AlphaFold. AlphaFold makes predictions of protein structures from amino acid sequence. You can make hundreds of millions of predictions at very little marginal cost, whereas there's only hundreds of thousands of lab-based structures. So now you could say, well, let's try to think about using AlphaFold for science. We've seen a Nobel Prize, obviously it does do a lot of things for science, but it can make some egregious errors, and I want to show you where those are coming from. It's not just hallucinations. It's more serious in some sense. Here's an example of a study that was done in 2004 in biology. People were asking proteins that have quantum disorder. Are those active in the cell? Are they used by biology? What's quantum disorder mean? Well, mostly proteins like to fold up. Occasionally there's some quantum disorder and there's kind of strands hanging off, like your hair. Does that mean it's a broken protein? Well, these people in 2004 said, no, maybe not. Maybe those strands get used somehow. So they said, let's just do a test, a hypothesis test. Let's take all the data in the protein data, make every protein known. Let's do a 2x2 table. Quantum fluctuation, yes or no. Phosphorylation, yes or no, which means it's active in the cell. You take all that data and reduce it to a 2x2 table, and now you do a statistical hypothesis test. You form the odds ratio, and you say, is that significantly different from 1? So are the entries on the diagonal bigger than the off diagonal, statistically significantly? So they did that, and the confidence interval they got for the odds ratio was quite big. They didn't have that much data, and it covered 1, so they couldn't make any conclusion. Fast forward 2022, someone said, let's just redo this with AlphaFold. AlphaFold is generating fake data, but it's really, really high quality. It's the world's best predictions. And it's true, very good predictions out of AlphaFold. They did that, and they got a very narrow confidence interval, and they said, now we can make a decision. All right, and this is happening, this is often called AI for science. Here's the problem. Okay, so we redid this whole thing. We took all that data and all the AlphaFold output. We took half of that and calculated ground truth and held that out. And we redid the whole experiment on the other half. The ground truth is the dotted line. You can see the odds ratio seems to be bigger than 1. In fact, it's more like 2. But the confidence interval coming from the AlphaFold output is that gold region. It's tiny, very, very narrow, meaning you're really sure of yourself that the number is around 3. Okay, the number is not at all around 3. You're not covering the truth at all. Okay, it's a huge bias. You can say, forget AlphaFold, let's just use the existing data. It's 20 years later. Now we have 100,000 data points. Let's just get a classical confidence interval. That's the gray region. So it's still very big, and it still covers 1. Long story short, our new procedure, we call it prediction-powered inference, fixes this. It allows you to take a true statistical confidence interval and shift it using the AlphaFold output or the machine learning output. So it's debiasing the machine learning output for confidence intervals, i.e. for decision making. Why is this happening, first of all? Well, after we saw this badly, biased confidence interval, we said, well, let's go back and look. Let's look at the AlphaFold output for quantum disordered proteins. Well, on the left, you have a particular prediction from AlphaFold. On the right, you have the true structure. And you can see in the true structure, there's quantum disorder. AlphaFold missed that completely. And that happened enough that it got this huge bias. Now, that's kind of a hallucination, quote unquote. Why is it happening? Well, because AlphaFold was trained on all of the past data. Most scientists are not interested in studying the past data. They're interested in being on the edge of science. So they're going to study some phenomena for which there's not that much data. They don't know that AlphaFold's actually not so good on that part of the problem. So they just run it, naively use it, throw it in, call it AI for science, give a very narrow confidence interval, and publish. Okay. We did this on a huge range of other problems. Well, huge, sort of a dozen. This is published in Science if you want to see the article. Here's a gene expression problem. Just, if you'll see that, you can barely see it. But on the right there, you can see the machine learning-based confidence interval again. It's not covering the truth. The new green one is covering the truth. We have a theorem. The green regions always cover the truth with up to some asserted confidence. Here is another example, which I really like because it shows that this is an honest method. This is just some kind of prediction of insurance coverage kind of thing. The machine learning-based confidence interval is that little gold region. It's really narrow. It's very sure of itself, and it's completely wrong. Completely wrong. The new interval now, the green one, is smaller than the classical statistical one, but not by much. And that's natural because it's using a very bad machine learning biased method. Okay? So you don't create something from nothing. Okay, I'm not going to explain in this talk how I do it or how we do it. This is a little bit of mathematics for those who are interested. This is for the M estimation kind of setting. You write down an M estimator, you add and subtract a certain quantity, you estimate what we call a rectifier, which is a debiasing operator on confidence intervals. Okay, so it's a little bit different from things I learn in statistics, and it is applicable to these machine learning systems. You can take any black box and you can debias it in this way. What you need is the black box plus a few hand-labeled predictions, not huge numbers, but a few hand-labeled predictions for your particular problem. And you can now do the mathematics and do this. Okay, so that was a little bit on bias. Everyone talks a lot about bias. That to me was at least a piece of serious science that sort of says how you can talk about bias and rectify it critically. Next thing I want to turn to is something we call statistical contract theory. So now it's going to be about bias and actually information asymmetry, and it's going to do that in a statistical way. Information asymmetry in economics is not done statistically, but we're going to do that here. So again, acknowledge my colleagues, Stephen and Michael and Jake. Briefly, the theory of incentives in economics. Incentive theory is kind of the inverse of game theory. Mechanism design, incentives, kind of similar parts of the space. Game theory says if you write down a game of some kind, it will have a stability concept like Nash equilibrium or Stackelberg. That'll give you an outcome. What if you want to go the backwards direction? Say, here's a desired outcome. What game do I design to get that outcome? That's called mechanism design. Okay? If it's a symmetric setup where all the players are symmetric, Nash equilibrium is the natural concept. The inverse of Nash equilibrium is auction theory. And that's what the algorithmic game theory people focused on. A lot of economics people are not so focused on Nash equilibrium anymore and auctions. They're focused on asymmetric situations. I have a leader and a follower. The leader decides something. The follower gets to see that, and the follower gets to do something. The leader could anticipate what the follower is going to do, and therefore there's game theory. These are called Stackelberg equilibria, the stability states. The inverse of Stackelberg equilibria is what are called contracts. And what are contracts? Well, they're basically, I'm trying to price something, for example. I have some service to offer, and I'm going to price it. If I knew your willingness to pay, I could price it just below your willingness to pay, and I would get all your, you'd pay for it, and I'd get a high price. I don't know your willingness to pay. And suppose I'm doing this like I'm an airline. This was where this first arose historically in the 80s. Airlines were in that era giving one price for every seat on the airplane. Amazing. And they couldn't price it very well. If they priced it too low, the airline would be full, but they'd lose money. If they priced it too high, the airline would be empty and they wouldn't make any money. So they were dying. And someone came along and said, no, let's do contract theory. Contract theory says I'm not going to have one price for everybody, but I'm not going to do just price discrimination. What instead I'm going to do is I'm going to have a list of options: price, service, price, service, price, service. And I'll adjust those, cleverly, so that I'm going to show that same list to everybody. And I've adjusted it in such a way that some people will look at that list and they say, I like that service at that price. Someone else will say, I like that service at this price. Your willingness to pay will be used by you, not by me, to decide which service you like. And I'll get income that varies according to willingness to pay. That's what I want. This saved the airlines in the 80s. We wouldn't have airlines to this day if they didn't do this, whether you like it or not. And this led to a whole mathematical field. Principals and agents. You probably have heard this language. It's another word for followers and leaders. All right, so we have this notion of asymmetry of information. You have a knowledge, which is your willingness to pay. I don't have it, but I want to transact with you. That asymmetry of information is uncertainty. It'll never go away just by sampling. Okay? All right, so here's a domain where this problem comes up. That's not just airlines and money. Clinical trials. We spend in the US tens of millions of dollars a year on clinical trials in every area. This is an asymmetry of information problem. The Federal Drug Administration is the leader. It's doing the decision. The pharmaceutical company has more knowledge about a candidate drug that's being evaluated. They were the ones who sent it in, and they know something about it. The FDA can't just say, tell us how good it is. They'll say, well, I don't know. And moreover, they will not tell all the information they have. Like, they worked on it in the past. They know something about it. They can't just give that to the FDA. So it's asymmetry. The FDA are a bunch of really good statisticians. They do a hypothesis test. Drugs should go to market, yes or no. All right? And they set it up so the false positive rate for any candidate coming in is like less than 0.05. Right? False positive means a candidate comes in, it's not actually an effective drug, but it goes to market nonetheless. You don't want to have that be a big number. They make sure it's small. They also have the power be high, which is drug comes in, it actually is effective, it should go to market, it does. Right? Now, no one knows whether these drugs are effective. How do you learn? Well, you do a clinical trial. Clinical trial, tens of millions of dollars. Right? What's a clinical trial? Roughly, it's just causal inference. You take 20,000 people, you give 10,000 people the vaccine, you give the other 10,000 no vaccine, you compare how their health is after a month. And we all watched this roll out the last year. It's very important. Okay, so we're going to now try to fix the problem. Actually, I didn't get into the problem. Here's the problem. If there's a small profit to be made, then incentives don't matter that much. It costs you $20 million to run a trial, and suppose you make $200 million if you're approved. The CEO can look at all the numbers on the page and do a little calculation to say, if my drug is actually not effective, theta is equal to 0, my expected profit will be minus 10 million, just using the numbers on the page. And she will go to everybody in the company and say, only send in drugs if you're quite convinced they're going to be pretty good. They're really good, because otherwise we're going to lose money. So they do that, and mostly good drugs get sent to the FDA, who does a good approval process, low false positives, only good drugs go to market. On the other hand, many drugs are much more than 200 million in profit. So 20 million to run the trial, 2 billion if approved. Now the CEO can do the same calculation, and she will see that my expected profit, even if the drug is not effective, is 80 million. Now she doesn't know if the drug is effective or not. That's the whole point of the clinical trial, right? But she goes to everybody in the company and says, send in any candidate you can, because even if it's not good, it'll pass through because there's a false positive rate of 0.05, and we'll get some drugs through, they'll go to market, and they're not going to hurt anybody. Theta is equal 0 doesn't mean it harms people, it just means it doesn't help very much. That's okay. Ethically, you can discuss, but. So the company now sends in lots and lots of candidates. The FDA ends up putting bad drugs on the market. And sort of this is more like what's happening. Okay, so we think this is a contract theory problem, but it's a statistical contract theory problem. And that's a new terminology that we have introduced. Statistical contracts, just briefly again, I'm not getting into details. Here's one. An agent is presented with a protocol. They can opt in or opt out. If they opt out, they just walk away, no harm done, but the mathematics will take that into account. If they opt in, they pay a reservation price R, like 20 million. Then they get to choose a payout function. What's a payout function? Well, it's like the terms of the license that you have. Okay? It determines the details of the utility functions. Okay, so that's classical contract theory. We design the contract. That's a list of, service price, like business class, economy class, and so on. Service price, service price. They pick something out of that list. They use their knowledge to make that choice. Now we run a clinical trial. That's step 3. Clinical trial samples data from the world. P theta is the actual real world that none of us know, but nature knows it. That's a clinical trial. Then we take this value Z, the outcome of the clinical trial, we put that into F, and that's the payoff for the agent. And the agent anticipated what Z was likely to be by their choice of F. They get paid off, and then the principal gets utility that reflects that payment and also reflects the true state of nature, theta, because eventually the FDA will look good or bad over time. All right, so that's what we call a statistical contract. And now you can analyze this by blending the tools of equilibrium, Stackelberg equilibrium theory, and statistics. You just blend them together in a mathematical analysis, and we've done that. In this analysis, you have to introduce the idea of incentives. Incentives are, here's our incentive in this particular case, which is the expectation under the null hypothesis, it's in the gray box there, Z from P theta naught, of the amount of money you make minus the amount of money you paid, F of Z minus R, has got to be negative. If it's positive, you just make money from nothing. The FDA wouldn't tolerate that. And now we have a theorem which says that a contract is incentive aligned if and only if all the payoff functions are E values. An E value is a concept that's been introduced recently in statistics. It is a random variable that's non-negative whose expectation under the null hypothesis is less than or equal to 1. So think of it as evidence against the null if it's bigger than 1. It's like a p-value, but it's actually nicer to work with. But moreover, we prove that a contract is incentive aligned if and only if all the functions in it, all the licensing terms of it are E values. They have this particular statistical property. Okay, I'm going to skip this next part. I want to move to the end here. Everything I've talked about is frequentist. You can also ask about what if I'm Bayesian? I have a principal who wants to do Bayesian inference, but they don't have a prior. On the other hand, this agent over here knows more about the domain. They have a prior. Okay? The principal can't just ask the agent, give me your prior. They might lie. And they can't just get data. They might lie. Instead, they can set up a contract and they can implicitly see by the choices of the agent, they can leak over some information about the prior. Okay? So we have turned that into a Bayesian version of this problem where you write down a protocol. It's not just a piece of mathematics, it's an actual protocol. You choose something, you do this, you do this, you do this, and you opt in or you opt out, and so on. And after that protocol has been run, you can do a Bayesian calculation from the point of view of the principal using numbers that are all known to the principal, and nonetheless, with no prior, do Bayesian inference. So if you're a Bayesian, you might find this interesting. I'm going to move to the end here. I'm not going to return to this. I want to have a little time for Q&A if there is. Just to say, if you're interested in this 3-letter market, you'll see a paper where we go through the analysis. And I want to just sort of say there's some mathematics, there's some utility functions. And at the end of the day, there's one particular term in the utility functions. It's a beta coefficient, which weighs two things, how much I care about this versus this. That one coefficient, when you do all the equilibrium analysis, is something a regulator can look at and say, if that number is below something, then more privacy is good for the overall population. If that number is somewhere else, privacy is bad for the overall population. And this is the kind of thing that you do not see in like GDPR analyses and privacy analyses by the government, but our approach allows it. Okay, so I'm going to skip the slides that go over that. There is an equilibrium characterization, and there are privacy regulations that you all know and love by clicking boxes about cookies. We're able to give some mathematics that supports particular analyses of these things. And let me just finish with this last slide. I'll just leave it up for a moment. I don't think AI is the right terminology for the era. It's not that we're building this superhuman thing that takes in data and gives out answers. It's rather that we're doing something like a new engineering field. Every 50 years or so, we have a new engineering field emerging. Chemical engineering took the interaction of molecules, turned it into an engineering field. Electrical engineering took the interaction of electrons, turned it into an engineering field. We are taking the interactions of humans and data and turning it into an engineering field. AI is a terrible terminology for that, but I lost that battle long ago. Thank you.
Thank you for the super interesting talk and the kind of perspective that you have on recommender systems and AI. Maybe it's a little bit time for questions. There's actually multiple questions about the, like your comments that you made on regulations and AI.
How does what?
On regulations, AI, and the market. Let me paraphrase them a little bit. You said that the regulation should like attach to the market. What are the implications? How do we actually implement that in the systems that we build, right? Eventually, our systems are going to make decisions that need to comply with these regulations. So how do you see that relationship between regulations, the market, and the systems that we build?
Yeah, so first of all, I'm not an economist. Part of my pitch is to bring economists in the room when you start talking about regulation. We can't make it up ourselves. But secondly, if you're going to regulate, you need to regulate the level of equilibria. And the whole talk has been about what are the equilibria? We find them. And when you see the equilibria and you start moving some things around, the equilibria will move. Do you like that new equilibrium? Is that good for social welfare? Is it good for each individual? Is it fair? Do the things that humans want? Are all the utility functions respected? Then fine, regulate and move it over there. Don't just regulate algorithms and data and all the things on the ground that we all talk about. Regulate the equilibria. And so that last part of the talk, which I kind of skipped, was there's two kinds of companies, high cost and low cost, and if you set beta to a certain value, that kicks out all of a certain kind of company. That's what's happening to GDPR. GDPR is a massive sledgehammer, just sort of no data flow, that kills the companies in the middle. And now people are actually seeing that happening. Bad regulation as far as I'm concerned. Maybe it was necessary, but it would have been better to think about what's the actual market here, what are its equilibria, and if we change something, how will that change the equilibria?
All right, thank you very much. We are out of time, but I hope people can corner you during the coffee break.
Sure.
Very good.
Happy.
Thank you again.
All right, thank you. Thank you.